So a very good afternoon, everyone. This is our first lecture in this lecture series on signals and systems. And well, we're going to be having we're going to be tweaking the process rather. We have quite a number of videos online, which you could review. Those are interesting resources. And but in this series, we'll try as much as we can to make things a little practical. So as we progress in this lecture series, we'll be playing with MATLAB and Python. Okay, so we'll be doing a bit of MATLAB programming and alongside Python programming. So we just play with both. So as you progress in your academic journey in electrical engineering or biomedical or systems engineering, you should become more comfortable using those tools. Okay. So we'll try to introduce them here if you don't play with them already. So this is the teaching plan which we already sent to you. Well, there's nothing new really. So we have core objectives. So I will just run through these objectives. Okay. So here we want to represent and categorize systems and signals. So all we're going to be doing in this course is signals and systems, or systems and signals. So we want to define them, we want to know how they apply. Then we'll talk about convolution. Then we'll see how it applies in the continuous and discrete sense. Then we'll also try to analyze some signals. So we'll do a little Fourier series expansion and then an analysis. Then we'll also talk about transforms, okay? The Fourier transform, the Laplace transform, the transform, and then we see how they differ, okay? Though when we talk about periodic signals, then we want to go series and just like that. So we'll come to that much later. And then we'll also try to look into some of the critical applications, okay? Now, signals and systems is an important course, very important, as it cuts across the engineering discipline. And along the line, some of you will go way into image processing, some speech processing, computer vision, machine learning, digital signal processing. Now, the idea is this: be it picture file, audio file, whatsoever it is you want to process. Some point, we should be able to relate with those things as either systems or signals, okay? And here's the course contents. And we have some materials. So, well, I have one core material here. That's my own material, AE Iraze, Signals and Systems. There's a playlist for Signals and Systems, in YouTube. So once you click on that link, then to take you to that channel. So there are quite a number of videos. So I'll suggest you try as much as you can to play with those resources, And if there's anything you want us to improve upon, or you've got some questions, drop them in the comment section, then we should be able to attend to them. Then you have some other interesting materials, and this is one good material you could also play with. Okay, so we have week 1, week 2, week 3, week 4, all the way. And well, the goal for this semester is to adopt the active learning strategy. And if we have to do active learning, then it means we have to be in groups because we want to do some kind of think, pair, share activities. And well, we'll try to see if in subsequent lectures, we'll be able to come up with some breakout rooms where, you could just sign in. But the major challenge we are having, or we will be having, is, managing the massive crowd. It's a large class. Sure, we should be over 300 plus or close to 400, if not more. So we may have to devise a strategy to encourage you to learn independently, okay? Interestingly, you've got some resources, online, and I'll also prefer you to learn independently. So we should be doing some in-class activities, okay? Well, that's that. So your assessment is going to cut across your CA and examination, okay? So we may adopt the 40-60, so that your in-class activities will be graded. Then we'll also try to have a written assessment to make up for the 40 marks, then 60 marks should go for the examination. So before I progress, it would be good I meet with you for the first time. So do we have any questions? Is there anything you want to find out from me right now before we delve into the business of the day? Do we have our class reps in class?
Yes, sir. I'm present, sir. Good
Okay.
afternoon, sir.
Good afternoon to you. So is there anything you want to know right now? Do you have any question, or is there any detail, any misconception, any transferred ideology, probably from some other persons you want us to clear right now before we begin?
Personally, sir, I have no questions. Well, personally, I have no questions, sir.
Okay. Okay, so you've got no questions. So everything is good to go for now, right?
Yes, sir, for now.
Okay. Okay, so I've got about 38 responses here. So if you're in class, kindly log in your presence. So you want to specify your department, your matriculation number, and your name. So that will serve as attendance. So if you did it before, try to do it again so as to update the record, okay? Just do it once and that's it. So if you're among the 30-something students here, you don't have to do it again, okay? Okay, so we'll just run through our signals and systems. Now, also, before we begin, I also want to get your feedback on the applications you are comfortable with. Have you guys been taught, or do you all know how to use MATLAB software and Python? Are you able to do Python programming? I need feedback from the entire class right now before we move on.
No, sir.
Not everyone, sir.
Okay,
Not
not
everyone.
Not all of us.
No, sir.
No, sir.
No, sir.
Not really, sir.
Not
Okay.
all of
No,
us,
sir.
Okay,
sir.
that's
Yes,
fine. That's
sir.
fine. That's fine. So I know the questions I'm asking right now, are they close-ended or open-ended? I know that you're just giving me a yes, no. So a yes to what, a no to what? Do you know how to use MATLAB, or have you heard of MATLAB before?
No, sir.
No,
You-
sir.
Some of us have heard of it.
Yeah, some of us have heard of
Not
MATLAB,
really.
sir, but
Okay.
most of us do not have to use it.
Yeah,
Once
most
you
of
heard
us
of it,
don't know how
sir.
to use it.
Okay.
Please, Wasabi.
Now, is there anybody in class that have played with MATLAB before? Please be comfortable.
No, sir.
You can't say no, you haven't. I just want to know, is there, okay, Ibukun raised hands, please tell us.
Yes, so I've installed the program and I'm currently working on, learning the syntax and how to run code on it.
Okay, on MATLAB, perfect. So that's good to know. In a class of over 222 right now, at least we have one person that, have started playing with the MATLAB software. Good. How about Python? Python programming.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, so
Yes.
okay,
Yeah,
okay. So let's say almost 100%, or let's say about 70 to 80% of those in class right now are comfortable with a Python program.
No, sir.
Yes,
No,
Yes,
sir.
no. It's only a few people that probably know how to use Python. No.
Okay, but well, it would be good, how to do so, because with Python, you've got a lot of libraries. You could do image processing with ease, computer vision, and all of that. Okay, so you could import one or two libraries and just, do your whatsoever, machine learning and all of that. So it would be good practice for everybody in this class to feel very comfortable using the Python, playing with Python, okay, Python programming. That's okay. Then for MATLAB, well, it's something we are really used to, especially in engineering. We try to do one or two things with the graphical user interface, and then with your M file, we also have the Simulink. So we drag and drop a few boxes and run your codes on them and get them to do whatever you want to do. But the idea is we try to model and simulate things, okay? And that's the idea, we want to build from this course. We just want to project that ideal, okay? So everything around us is a body of signals and systems, okay? So life itself is all signals and systems. Now you where you are right now, just understand whatsoever you're doing right now is all signals and systems. Now I'm talking, so whatsoever I'm saying right now translates to some signals that is being processed through the platform I'm trying to communicate, right now, and then you get it. So I'm transmitting here and you are receiving somewhere. So the entire process, or the system that enables this, or the idea that enables this transaction, is the system. Okay. And then the fact that you can hear what I say, and I can also hear, what you say, then we know we are dealing with signals. But at some point, we have to now classify these signals. Okay. So I'm talking from the analog perspective right now. But for you to be able to interpret what I'm saying right now, like most of you can, and already interpreting because you can hear me clearly and you're able to process these things, is that this signal, which is analog from my end, have really gone through some kind of rigorous processing. And there's a system that actually performed that operation. Okay, right from my computing device to the communication network to your own device and all of that. So long you are communication enabled, you will be able to receive the signal. But mind you, this signal really went through a whole lot. Okay, so modulation, processing, so there's a whole lot of signal conditioning going on. Okay, and then you get the signal undistorted. Okay. And we really, don't appreciate what is going on. You pick up your mobile device and you say hello, and someone says, yeah, I'm here. What do you want me to do for you? Now, we don't appreciate the fact that there is a system behind that transaction. And that system is built in a big box of complexities. And what we call complexity is really not complex because they are just simple components we put together. But because we have put up quite a number of simplified or simple components, we now say, well, this is complex because it's now massive, okay? So, well, we are going to be looking at things from the perspective, from the simplified perspective. So by the time we begin to put up the building blocks, the simplified components into a massive building block, then we cannot have a very complex system. Okay, so we do not interpret from the complex dimension. Okay, so like I always say, I would love to once again invoke the Occam's razor. Okay, so the simplified approach is usually the preferred approach. Okay, so we want to try as much as we can to keep things very, very simple. Now, I understand most of you have looked through the lecture notes online, and some of you have even gone way ahead of our class. So we'll try to make things a little interactive this time. Then I'll try to pull up the MATLAB platform to show you how simple it is. You know, so we're going to look at it from the very, very basic application zone. Then as we progress into the course, then we'll see if we'll be able to do some machine learning, computer vision activities, and all of that using the Python platform, okay? So where we'll be able to import some libraries, and so you want to install these applications. For your Python, you could install the community edition, but if you have your institution email, you could request for the professional edition where they'll give you your license, okay? And then your yearly or annual license. Then for your MATLAB, our institution, the University of Lagos, have a functional license. So you could liaise with I think a CITS, yeah. So they should be able to, put you on that. So you're able to install the latest edition, okay? So we have a whole lot going well for us right now in the University of Lagos, okay? So I'll appeal that you all take advantage, okay? So, so let's get this out. Okay, so good. Now, we want to introduce signals and systems, and I don't think I want to bore you with so much jargons, okay? So let us start with what you know, okay? So I want us to begin. I know we have biomedical engineering, we have electrical engineering, computer engineering, then we have systems engineering. So I want someone in class to define a signal, or better still, tell us what you know about signals and systems, just before I begin. Go ahead, please.
Signals are just abstractions. Okay. Yes.
Okay, the abstractions.
Abstractions of any measurable quantities that is a function of two main fundamental variables, which are time and space.
Okay.
While systems,
okay,
anything that accepts input variables, process and operates on it, and produces an output variable.
Okay.
An output signal, sorry.
What's that now? Can you repeat your last statement?
Okay, a signal is just an abstraction of any measurable quantities that is a function of two fundamental variables, which are time and space, while a system is anything that takes in an input signal, operates on it, and produces it as an output signal.
Okay. Introduction to signals. Perfect. Thank you so much. Signals and systems. Perfect. You just gave us the perfect explanation. Now, does anybody have any contrary view or addition to what?
Good afternoon, sir.
Okay, good afternoon.
A signal is
Please tell
a
us your name and go on.
Obiasog Michael. I'm a D student.
Okay, go ahead. These students, biomedicals or systems electrical?
Computer engineering.
Computer engineering. Okay, go ahead, please.
A signal is a description of how one parameter changes with another, while a system is a process in response to an.
I didn't get that. Why system is what?
A signal is a description of how one parameter changes with another, while a system is a process that produces an output signal in response to an input signal.
Okay, perfect. So this.
Can I say something else?
Okay, go ahead, please, Samuel. I can see your name.
Okay, sir. My name is Samuel. I'm a computer engineering student as well. A signal is more or less the result of two interactions between two or more variables, right? For example, in a light switch, you have two variables, 1 and 0. So pending the action on the light switch, it triggers what do you call it? It triggers a process which now happens in the system, which is now the circuit that is being operated in the light switch. So a system is more or less how do I put this? A system is a collection of different departments or compartments of, or rather, different departments or compartments that make up a whole unit which process and give out information or results based on the signals fed into them.
Okay, perfect. Thank you so much.
I'm sorry, I have something to say.
Okay, go ahead, please. We have someone else?
Yeah. My name is Tomo. I'm also in computer engineering.
Okay. Go ahead, please.
A signal is the process or result of transmission of data from one body to another. While a system is the internal circuitry that performs the transmission of data or transmission of signals from one body to another.
Okay. So I would love to get clarity. You know, if I can mention transmission with the signal, and then in the system, you said a system is something that enables the transmission. Can you clarify, please?
Okay. A signal is like a wave of frequency that moves from one body to another.
Okay.
That is the transmission of the data. So in the system is what allows this signal to move from one body to the other. The system is the body that moves the signal,
Okay.
or inhabits. The system is the body that inhabits the signal.
Okay. Can the signal be stationary? Because if you're just likening the signal to be in motion, right? Can a
Yes.
signal be stationary?
I don't believe so, sir.
Okay, I believe so. Have you heard of standing waves?
No.
Okay, so
Interference.
Interference, well, at some point they could cancel that at some point. But the point is, I understand your point. There's some level of oscillation. So you're saying that a signal is only a signal if there is oscillation.
Yes, sir.
So does oscillation most of the time translate to movement? That's what I'm asking. So, well, we're going to come to you shortly. Oriaku David, your hands are still up. Please don't lower it yet. Because now we are looking at oscillation. Can we have oscillation in a stationary point? Can something oscillate between fixed points? recall your physics, right? So let's assume I have a point here, I have a point here, then I have a string. Then I pull this string upward. Then before you know it, it begins to oscillate, right? So it first goes this way, then it goes this way. Then depending on the pattern of oscillation, then before you know it, it begins to oscillate. But at this point, it cannot exceed this, you know, but something is changing, right? But it's at fixed points. Okay, so if, for instance, I have in a pool, then I have a signal transmitting this way, then I have another signal transmitting this way. So at this point, what do we say is happening at this point? Somebody mentioned interference,
Interference.
right?
Superposition. No, it's interference.
Yeah, somebody says superposition. So someone could also begin to liken this to some transmission. And then somebody can also begin to talk in terms of standing waves. Okay, so when you're talking about transmission lines, so if we are having standing waves, does it mean it's no more a wave? And if it's a wave, can we say it is a signal? So if signal must always be in motion, so what happens to standing waves? Do they cease to be signals? Well, I'm giving you that as an assignment. Probably in our next class, you want to give us your findings, okay? So now, David, thank you so
Sorry,
much
sir, come
for,
again.
thank you so much for your contribution.
Sorry,
Well,
sir,
I
please come
said,
again.
okay, I said, well, now that he said, you know, a signal must be in motion. So I just said, well, we have standing waves. So if waves are signals, so we want you to confirm. I want you to go make your findings now. You want to research, okay? So are standing wave signals? So if wave must be in motion, or can we have stationary waves? And if we call them,
Yes, we have stationary waves.
so if we call them stationary waves, can we say they are still signals? And what make them signals if they are still signals? So if a signal is in motion, fine. But what if the signal is not in motion? And what can make a signal not to be in motion? So you want to tell us that. So you go figure that out. You know, that's why self-learning. So whatsoever you find, your findings would interact in our next class. Okay. So thank you so much. So let us move on. So we have Oriako. Go ahead, please. Share your thoughts.
Okay. A signal is a function or a dependent variable of one or more independent variables.
Okay.
While a system is a meaningful interconnection of physical devices and components.
Okay, interconnection of components. Okay, beautiful. So let's go to Ibukun. Tell us.
Okay, so I wanted to speak on the standing waves points, not the signals and systems.
Okay, go ahead.
While you were explaining standing waves, and you sort of brought out a question that are they in motion, right? So I just wanted to say to that they are moving, like there is energy, there's a sort of, let's say, propagation of energy, but the difference is there's no permanent like displacement. They return to their starting point. Like a wave generally moves things with displacement, but with a standing wave, there's no displacement. So that just what I wanted to say about that.
Okay. So
Oh, sir, I also want to do something.
okay, yeah, before you go on, so are you trying to say that a wave, a signal must be in motion?
Yes.
I believe that question was
Oh,
directed at me, sir.
Is what?
Was that question directed at
Yeah, go
me,
ahead.
sir? Oh, okay. Well, my personal opinion is yes. Um, standing waves must be, sorry, signals must be in motion in the sense that there has to be a signal has to try.
Your line is breaking, please.
Sir,
Go ahead, please.
To another. So I don't believe a standing wave is, from my knowledge right now, I don't believe it. Sorry, did you get that, sir?
No, I didn't get that.
Oh, okay. Just to summarize what I said uh, that I believe standing signals have to transmit information, and a standing wave doesn't really transmit information. All the information that is generated is stationary.
Okay. Okay, fine.
sir,
Sir, I disagree kind of.
Okay,
I
go
kind of
ahead.
disagree.
Go ahead. Let's say
There was a statement that Ibukun made that stationary waves are, I think he said they are in motion or something like that. And he said that yes, signals must always be in motion. The second part of that is true. Yes, signals must always be in motion. There is a reason why stationary waves are called stationary. Yes, there is energy propagation, but there is no translation or motion involved. There's a reason why they are called stationary. And also it depends on the method of propagation of the wave or the system in which the wave is being developed or created. So like I said, depending on the system, since you're talking about signals and systems, depending on the system, the stationary wave can't transmit signals, or rather, a stationary wave cannot be a signal. A signal is only, what makes a signal truly a signal is if there is motion, like communication between two different parts of the system that transmits the signals to the
Samuel, I agree with you.
Okay, thank you.
Okay.
Thank you. I will let, just hold on. Hold on. I'm going to let you in, Michael Obi. Okay. Now, just before I, let Michael Obi in. Now, have you seen a picture file before? A picture file. A picture file. Now, I can see something on Michael Obi. Is this avatar? I don't know. I can see some pictures on Samuel Alozie have a footballer, Now, are these signals?
Yes.
Are they in motion?
No.
Okay, now, that's where I'm going to. Now, all signals must not be in motion. Okay?
Yes.
So I just pulled you out of that assignment. Okay, all signals must not be in motion. Beautiful. We come to standing waves because we have two waves traveling in opposite direction, and then boom. So we now begin to deal with propagation, the propagating wave and the standing wave. Well, that's when we begin to talk about transmission lines and all of that. Okay, but well, all signals must not necessarily be in motion. Okay, all signals must not necessarily be in motion because I just mentioned a particular signal. So we're going to talk about what makes a signal then, okay? But motion is very important when we talk about signaling, okay? When we talk about signals. Motion is an important parameter when we now begin to play with signals because without motion, we may not be able to talk about transmission. Okay? But when we talk about a signal, we want to talk about the relationship between some dependent and independent variables. Okay? So I need you to begin to cast your ideas in that regard. We are talking in terms of some dependent and independent variables. Okay? So if there is no interaction between some dependent and independent variables, we cannot say we have a signal. That is why a direct current is not a signal, although it is in motion. Do you get that? Did you get that?
Yes, sir.
Yes, sir.
Yeah. So direct current, yes. Well, it's not a signal, but an alternating current is a signal. So because the direct signal is literally constant, right?
Like it's not moving.
It's constant. Let's leave it at that. Okay.
Okay.
Yeah, let's leave it at that level because we can now go into some level of motion and variability are two different things. I want us to get that cleared, please.
Okay.
Okay, you know, when we talk about motion and variability, they are two different things. Does that make sense, please? Because I need us to clear some misconceptions before we begin to talk. Because when we talk about direct current, what is a current? Because I remember I told you guys to look up the videos on the fundamentals of electrical engineering, where it's going to be twofold. It's going to help in this course, and it's going to help you in your circuit course, okay? I used to be in that team before I pulled into this signals and systems. So those are materials also meant for your fundamentals of electrical engineering. So I want to believe they are a little simplified, but I didn't make up all the notes, except I get that request from you guys to make up all the notes. So I know some lecture notes are not there yet. I just had to pause at some point. But I want you guys to look up those notes as well. They'll help you in that course, and they will also help you in this course. Now, when we talk about current, we talk about charge in motion, right? Hello?
Yes, sir.
Yes, sir.
Yeah, so it
Yes,
means,
sir.
it means direct current is in motion. But the fact that it is a constant value in motion because the charges, now, when we begin to separate charges, we have current, right? We have voltage.
Yes, sir.
Separate charges. So, but when the charges move by way of that separation of charges, we have what? Charge in motion. So we say charge in motion is current, right?
Yes, sir.
Okay. We say, let's get this pen back. Okay. So we say current is charge in motion, right? So, but when we talk about separation of charges, we say this is voltage, right? Now, the fact that the charge is in motion does not make it a signal, okay? Because for the direct current, this is a constant value, okay? As we are progressing in time, the value is not changing, so it is constant. Say A, okay, is amplitude value. So you now see that by the time we move at the first time instant T1, we have the same value. We move at the second time instant T2 is the same value. We move at the third time instant is the same value. We move at the nth time instant is the same value. But is the current in motion? Yes, it is in motion. So the fact that the current is in motion does not make it a signal.
Sorry, sir.
Go ahead, please. Go ahead. Go ahead.
This looks like the deterministic signal. The direct current graph looks like the deterministic signal. What's the difference between the two?
Okay, well, I'm going to come to that shortly. Okay, so when we talk about something is deterministic, it's not probabilistic. So what does it sound like? What does that sound like? Say this is deterministic.
It can be determined.
Exactly. Okay, so it means we can actually tell the value at a specific time interval. Okay, So
Yeah, it's essentially a function.
yeah, it's a function. So something like this. Okay. So the annotation, yeah. So something like this. So we can know the value at this point, then we can know the value at this point, then we can know the value. This is absolutely deterministic, okay? So this may look like a DC, but at this point, you know, it drops, right? From a high state to a low state. Okay, so this is a digital signal, okay? But if it should be a continuum, no. So at least we can tell the value at an instant. Not necessarily, it's not a DC. So at T, fine. But what happens after T1? So if the value should change, then we can say this is a signal, okay? So the fact that it is assigned a value at an instant of time makes it deterministic. But we equally have a signal that is a little probabilistic. So we cannot really tell what the signal is at a given point in time because it is really messed up, right? It goes this way, we have some signals like this. So usually for such signals,
random signal.
yeah, we use scattered plots, right? We just use scattered plots. We don't want to join the line.
Like the stock exchange.
And so we now have things like this. We call it scattered plot, right? But if we join the lines, it's all messy. Okay. So what am I trying to pull through here? Now, the fact that a particular function is in motion does not really make it a signal. Okay. Now, we only have a signal when some parameter is changing with respect to another parameter. So it means that one parameter must depend absolutely on another parameter. That is why the alternating current, which is also in motion, is a signal because the value is changing with respect to time. Does that make sense?
Yes, sir.
So, yes, sir.
Okay, so
Yes, sir.
it's just
Yes,
that,
sir. Makes sense.
well, interestingly,
Yes, sir.
I just ended up answering your assignment, right? Okay, so we will have another assignment. Okay. Oh, so interesting thoughts. I appreciate your views. They are perfect thoughts, excellent thoughts. And I would like to let you all know that you were all correct, you know. Now, someone may want to say, well, you just said a signal cannot be in motion. It's a signal, you just said, we can have signals that are not in motion. Yes, but that does not mean when the signal is in motion, it's not a signal. So the fact that you said, yeah, a signal should be in motion, you are correct. But we just added to what you said that, well, we can also have a signal that is not in motion, right? Okay, go ahead, Michael Obi. Tell us.
Okay, sir. So basically, from what you said, about a signal, you just listed three types. That there are one that is stationary, that is constant, like is not changing its position. Two, secondly, there are some that is moving. And thirdly, there are other like stationary wave. Those type of wave that are formed by like they move but they are not changing their position. They just have a fixed point.
No, not so, my friend. I have not said any of the things you said. I have not said these are the types of signals. But I
Okay.
know, but I know I have said that a signal that have a constant value relative to some other parameter is not it's not a signal. A parameter that is defined as a constant value with respect to some other parameter is not a signal. That's why I place this here. Let's change the color. I said this is not a signal, okay? DC is not a signal. Okay.
Okay.
So it can be part of a signal, okay? And I have equally not mentioned some types of signals too, because some of you mentioned some type of signals. Someone mentioned deterministic signal, right? So that's a type of signal. Right?
So all signals are AC.
No, all signals are not AC. Because AC is alternating current. Okay.
Okay. Okay.
Yeah. So we cannot say all signals are alternating currents. No. But
Okay.
all signals must vary with respect to some parameter. So we have a dependent variable and independent variable. And it must not be one, it could be one or more independent variables. Okay?
Okay, sir.
Yeah, so the independent variable could be time, it could be space, it could be some other thing you decide to define. Okay? But the bottom line is we have a function that is dependent. Now, you see, let's liken your position as a student with the University of Lagos. Now, your graduation is strictly dependent on the University of Lagos management. Do you believe that?
Yes, sir.
And on the union, on the whatsoever union that may enforce your the smooth running of your calendar, and the government, right? So we now see that you are the dependent variable, right?
Yes, sir.
What are the independent variables? The government, ASU, NASU, SANU, and all other factors, right? So now, if you must graduate, now those factors must put the necessary measures in place for you to graduate. That's what we mean. So you now see that your position as a student can be likened to a signal. So like I mentioned earlier, everything in life, to the food you eat, can be likened to signals and systems. That is why this is the most important of all courses you will ever have to take, because this is where the modeling of all forms of ideas and thought can be made. So once we are able to model a process, then we can design it, okay? So Ibukun, tell us, your hand is up.
Okay, thank you, sir. Yeah, so there's just something I was trying to get a grasp on,
Okay.
a sort of mental model, I'm trying to use to understand the statement you made about signals. So
Okay.
if I understand correctly, basically the key defining property or the key defining feature of a signal is that it must be able to convey information. Because you said a direct current is not a signal, because in my mind I'm thinking because a direct current cannot convey information because it has only just one state, right? So a signal must be able to take on multiple states. I just want to know if my line of reasoning is valid.
Okay, when we talk about information conveyance or transmission of information, we talk in terms of a system, not the signal. Because something will have to generate the signal that will be transmitted. Do you understand what I just said?
No, not really.
Now, so I want to transmit X.
Let's be older than you want.
Now, this X, I want it to come to this point where I will say it is Y, right? So that Y is the same as X, or better still, is the same as a distorted value. But for that to happen, X, we have to come into this, which we call the system. Okay? Now, for us to have X, something is going to generate it. before we send it over this link. And this link could either be wired or wireless, right? Like you know. Now this could equally be wired. These are the media, or it could be wireless, right? Now, for us to be able to also get this, if something is generated, and it means that this has to be recovered, right? Isn't it? So it means
Yes,
that
sir.
at the point where we have the signal, we must have a signal generator. At the point where we have to recover this, we must have something to recover it. And at this point, we talk in terms of transmission. We say, let's not write transmitter. Let's write, sorry for that. Let's use the word transmission. And here we have our reception, right? So this is our transmitter. This is our receiver. Okay. Now, and for us to be able to transmit whatsoever we are saying right now, the speech signal is very low, right? So we have to do modulation, right? We want to hide this low frequency in a higher frequency, right? This is what I'm sending, but I want to put it in a big carrier, which can be transmitted as a wave, right? And then if I'm going to do that, then at this point, I'm going to demodulate, right?
Yes, sir.
Demodulation, right? Okay, but what is happening here? This is a signal conditioning module, right? This is signal conditioning module. Some may call it your digital. No, let's not go digital or analog yet. Some may say your signal processor, right? Now, this X must contain the information. So let's say I'm transmitting X symbol. So probably if you want to get the full gist on this, you may want to look up the lecture notes on information theory and coding, right? So, so this X, you know, message will now have to contain the information. Okay, that it contains the information leads us to some level of uncertainty, which I don't want to go into. Okay, so that's where the Shannon information theory and all of that came up. Well, as you progress in your study, you are going to come to that. Okay, but the idea is this: we could leave this signal at this point where it is generated without transmitting it. It remains here. Now, I have so many things in my head right now that I would love to pass across. I can equally decide not to. Okay, so those are signals, really. But should I let it out, then it's going to go through to a system that will process it. Now, this system is more like a filter. Okay, it's more like a filter. And this filter is going to process the signal and all of that, and then hand it off. So the link that will be used to receive it, and you now recover that information. Well, I don't know if this gives you any information yet, or is there, you see, are there still some doubts I need to clarify before I move on to Rotimi?
I think it's clearer now. Thank you, sir.
Okay, okay. So Rotimi, John, so tell me.
Okay, good afternoon, sir.
A very good afternoon to you.
Yes, sir. So, sir, is time and space a wave?
Is time and what?
Space a wave.
Okay, time and space are some kind of variables. Let's put it that way.
Okay.
They are variables. So if I have to chart this up in a plot, I can call this my time or space axis. Then I can call this my X or Y axis. So when the parameter I'm trying to take as a signal is beginning to vary with respect to this time, which is the independent variable, then I say I have a signal. So I can upload.
Okay, sir.
Okay.
Okay, sir. Thank you very much, sir.
Okay. Okay. So beautiful, beautiful contributions. So it means you guys have been looking up the videos. So I'm really, 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 really impressed.
Yes, sir.
Yeah, I'm really impressed. That's good. So and hope the notes online are informative. Hope they are simple to understand.
Yes, sir.
Okay, so if they are, probably you
Yes,
also
sir.
want, so probably you want to also leave a comment in the comment section, you know, and give the video some likes and thumbs up, right? So if it's that, okay. So I have gr8_4_sure. So tell me.
Good afternoon, sir. How do we get the lecture notes? I've not been able to access them. The fundamentals of electrical engineering. How do you?
Oh, I actually made a lecture tutorial on that. Interestingly, I'm not in that team right now. I used to be in the team as one of the lecturers. So presently I'm not in the team. So my notes, I turned them into videos, which are uploaded in a playlist in my channel. So if you go to have you subscribed to my channel?
Yes, yes.
Yeah,
Okay, the playlist on the same Signal Systems channel.
Yeah, so there's a playlist on signals and systems. There's also a playlist on fundamentals of electrical engineering.
Okay. What of the information theory and coding?
There's also a playlist on information theory and coding. That's for your information if you want to. Yeah, if you want to at this stage, you can look up the notes, okay? They'll help you, get some beautiful insight. Yeah. Okay, so they are different playlists. There are different playlists in the channel. So, and if the videos, are helpful, just try to leave some comment, leave a like, and some thumbs up. That will help give the notes some ranking too. Okay, fine. So
I don't know about your channel, sir.
Okay, you don't know anything about the channel?
Yes, sir.
Okay, so you can just Google the name. Dr. Augustus Ehireme Iwaze on YouTube, or you can search on YouTube, or you could search on Google, then it's going to take you to the YouTube channel. So once you get to the YouTube channel, then you see all the resources there.
Okay, sir.
So actually group them into different playlists. So you can, just go into the playlist you want, and then you get some beautiful insight and information. So we have a playlist on information theory and coding. So we have some lecture notes there. Even the fundamentals of electrical engineering, we have some lecture notes there. Although I'm not one of the lecturers for the fundamentals of electrical engineering right now at the moment. Maybe in the future I'll come back to it, but at the moment I'm strictly on the information, but the resources should be helpful. Okay, should be helpful because I made them on demand one time for some students that requested I do that. They were struggling with the course, so I had to just do that, So that's fine. So let's come back to the business of the day. So technically, we have literally revised everything about this course, but there are still some interesting details, okay? So we started off with signals. What are signals? And someone just put it up the way we have it in the node. It's an abstraction. So, when we talk in terms of abstraction, it means it's an idea, right? So we can just say signals are idealized. We cannot really say this is how it is in real life. We just seem to idealize them. Then we'll create systems to represent them the way we have idealized them. Okay? So, and then we are able to pass some analysis, okay? So that's why it's an abstraction. And when we put it in that light, we also want to say it is a measurable quantity. It's something we can measure, okay? We can measure it such that we say, well, if we can measure that signal, so let's put this up against signals and systems. So when we say a signal, then we now say, well, this is a signal. If we can measure it, then this dependent variable must be a function of something, probably 2t. It's a function of time. Okay? So that this value, let's say +1, plus a constant. That is no problem. So it means we added a DC to the signal because 1 in this point, at this point, is a direct point, it's a DC value. So it means that this function, which is dependent, is literally a function of the independent variable t. So as we tweak the value of t, the value of the function changes. Okay? So since the value of the function f of t changes with respect to the independent variable, we say it is a signal. So the fact that a dependent variable will have to change its value relative to an independent variable makes it a signal. Then we now begin to compare some of those interesting things we have to play with in electrical engineering or in engineering technology or design. So, well, we know we used to have something they make mention of that says alternating current, and then we have something also they say it is direct current, where this is T and this is T. So what are we saying here? Then this is I of T, this is I of T. So if I of T, in this case, is the dependent variable, is it changing with respect to the independent variable T, time? For the AC, we say yes. But for the DC, we say no. Then this now brings us back to this definition. So it means that if the dependent function is not changing its value, it is not a signal. But it is a quantity. So all quantities are not signals. That's what we're trying to say. Okay? And that gives us some sigh of relief. And then we can now begin to describe variants of this signal. Because this signal that I just described here or here is single variable. What if it varies with respect to multiple independent variables? Say, I of t is now a function of, rather than this, is now I of t1, t2. Now, this becomes a multi-variable signal, while this is a single variable signal. Okay? Now, if the definition of a signal is clear, then we can now move on to talk about the classification of signals. Okay? So we have two broad categories where we talk about the continuous time signals and the discrete time signals. So we're going to do some, I'm going to move on to play with some of the MATLAB activities. Okay, so let us see how a continuous signal looks. If we want to plot it, then how a discrete signal looks. Now, okay. Now, we said for the classification of signals, we have continuous time signals, and then we also have discrete time signals. Now, these are the broad categories, okay? So oftentimes you see CTS for continuous time signals, then you see DTS for discrete time signals. So if it is continuous, okay, it could be analog or it could be digitized, okay? But the bottom line is whether it is analog or digitized, so long the value is continuous with respect to time, it is a continuous time signal, okay? And now, when we're not talking about the discrete time signals, it means that they occur at discrete time intervals, okay? So it could be this, could be this, could be this, this. So this signal is occurring at discrete time interval. And oftentimes we represent these signals with square brackets, okay? While we represent the signals with your regular brackets, okay? S of t, then S of n, okay? Because these are discrete values, okay? The n values, okay? So you must have heard of sampling. So this looks more like signal sampling, okay? More like a sample space, okay? So we'll come to that when we begin to play with the application. Now, in the same vein, we have systems, okay? We equally have systems. Now, when we talk about systems, just like you already said, we want to describe something that can take on the input and then give us an output, okay? And then we want to say, well, there are some kinds of systems everywhere, okay? Now, the human body is a complete system, okay? The human brain is a complete system. So for those in biomedical engineering, you could model the human brain as a system that can take in some responses, okay? Yeah, the heart itself, subsystems, the liver, the kidney, you know, so you want to do 3D printing so that, well, there's someone that needs a heart transplant. Can we print a heart, a 3D heart to replace that heart rather than look for a human being who is willing to donate and lose his life? So that's why you are in biomedical engineering. So you want to figure out how we'll be able to design that heart, how we'll be able to design some of those internal organs to retain those arteries, those, you know, little tiny veins in there, the mechanism and everything, the anatomic composition. So want to look into all of those connections. It's a huge circuit, more like your electrical circuit system. Okay, so the human anatomy is a huge circuit. We have all of those veins and all of those connections, and we see that all of these organs are connected somehow. Okay, and then they're all linked up to the spinal cord, and then they send signals to the brain. So they poke you a little, you feel pain, and then the spinal cord takes it straight to the brain, and it interprets and says, well, this is pain. Then you feel another form of touch, so, well, this is excitement. You know, so how is the brain able to interpret different kinds of touch to say, well, this is painful, this is exciting, this makes me sad, this makes me happy? Now, because it is a system. Okay, so that's where we're going though. Your mobile device is a system, okay? The computing device you're using right now to engage in this classroom is a system. So what makes a system is that it has an interface where we can feed in the input, and then it also, we also have an interface for the output. So this now, so with this, we can actually pull through for robotics, okay? Robotics and the likes, okay? Now, it is also an abstraction because we are relating with an idea, like I said earlier. Yeah, it's not, we cannot really say this is how it is in real life, but for ease of modeling, we have to tie it to an idea, okay? We know, well, it takes in an input, it's some device, so it must not be a box, but we know this is the system. And usually we describe this system by some impulse response, okay? So that once this acts on this is more like a filter, then we should get an output. But in real life, we do not expect to get a replica of the input. So we expect to get a distorted version, but we always target minimal distortion. So we have to find a way for near perfect recovery, okay? And for us to do that, Nyquist says something, okay? So we have to sample at a particular rate, twice the maximum frequency. And then there won't be the aliasing and all of it. But we'll come to all of those things later, okay? But let's take it in bits, okay? Just the same way we made mention of the broad categories of signals, we also have that too. Because if we have a continuous time signal, so obviously we want to have a continuous time system operating on that continuous time signal. Now, if we have a discrete time signal, we want to have a discrete time system operating on the discrete time signal. So we also have continuous time system, and we also have discrete time system. Okay. And one perfect example of a system that we are going to be talking about is the linear time invariant system. Okay, we call it the LTI. Okay, so it means it combines the property of linearity and the property of time invariance. Okay, so when we talk about linearity, so let us get this out. We're talking about LTI systems. So when we talk about linearity, it's simple. So it means that if, for instance, we feed into the system S1 of t plus S2 of t into the system, then we should get Y1 of t plus Y2 of t. So it's more like the rule of additivity, right? So because from this, we must have a system such that S1 of t fed into the same system gives us Y1 of t, and S2 of t fed into the same system gives us Y2 of t. So should we add these excitations, then it should give us this response, okay? Largely because this input fed into this particular system gives us a specific output, and this particular signal, when fed into the same system, gives us a certain output. Should we add both signals or input together, which we call the excitation, the same system should give us a response that adds their distinct values. Okay, so it means the property of linearity is obeyed. Now, when we now talk about the time invariance property of this same system, it means that should we have a signal that we shift in time, okay, then the output should also be shifted in time. So the implication is this, that when we feed this system with this signal, say at 1 a.m., should we feed the same signal into the system at 2 p.m.? We should get the same output. But if the output is affected by variation in time, we say, well, that system is not time invariant. So it means that the response of the system should not change as time changes for us to have time invariance. So this makes for a very perfect system that may not be practically realizable, but it gives us the basis for the approximation of models, okay? So that's what I just want to mention there, okay? The basis for approximation. But in real life, we do not have time invariant systems, okay? Because we have some level of non-linearities and time variations, okay? That is why if you take a particular device operating on Earth into some other space, like in the moon, it may perform different, okay? So, but the linear time invariance model enables some form of approximation for system design. Is that clear, please?
Yes, sir.
Okay, I just want to quickly run through a few details so that we are able to do, because I also want to introduce us to MATLAB today. If since most of you are comfortable with what's it called, Python, so it's what most of you use for business. So we just have to play with, we introduce the MATLAB. So I'll put up the MATLAB and then we'll try to implement some of these signals, okay? And then we should be able to make huge progress going forward, okay? Now, so to summarize, if we now have a linear time invariant system, say LTI systems, as we'll be mentioning as we progress. So if we have the excitation to the system, so the output, this system is characterized by H of t, the impulse response of the system, okay? Then the output Y of t should be the convolution of this input and the system parameter, okay? So Y of t being the response will be H of t convolved with S of t, okay? Now, in the time domain, we have this convolution. But if we should transform to the frequency domain, this convolution operator becomes multiplication in the frequency domain. Well, we're going to see that later, but just don't forget about that now, okay? So here, this is the applied input, which is the excitation rather. It is the excitation to the system. H of t is the impulse response of the system, while Y of t is the response of the system. Now, this part is what we worry about when we talk about synthesis. So I have an idea of how the output of a system should be. Then what should we do in terms of designing that system? So we want to check, is it going to be a first order system? Is it going to be a second order system? So you say the fundamentals of electrical engineering will introduce you to circuits, you know, so as you progress in your study, you're still going to take a course on circuits and systems. Then we should be able to synthesize. So say, well, this is this particular system will require us to have XYZ components put together, okay? So there we can now design the system, having an idea of, okay, how the input and output should be, okay? But basically, in our study, we are going to be doing analysis, okay? So we know what the system properties are, then we have the input, so what is the output? So we want to tell what the output is, okay? And summarily, like you already have in your notes, the signals and systems will cover areas in terms of describing signals as functions of frequency. Now, I know one of us, in this class made mention of frequency, right? So everything we get to talk about is frequency. So when we say bandwidth, we are talking frequency, right? So when we talk about a whole lot of things, we are literally talking about frequency. So, when we talk about channel, you probably must have heard of channel. Channel is still frequency, okay? So everything boils down to frequency. So these signals we are going to be talking about or describing or analyzing, just be rest assured that they are functions of frequency. Okay, and at some point, okay, go ahead, please. A Zoom user, can see your hand. You have the floor. You can unmute your mic. We can't hear you. A Zoom user, your hand is up. Can you unmute your mic so we hear you? Okay, okay, fine, okay. So then we also want to investigate how the systems respond to inputs of different frequencies. So I feed another input, so how is this system going to respond? Is it going to respond the same way or whatsoever? So we also particular about what is happening with the system. Then we also want to develop tools that will help us to switch between frequencies. I just made mention that, well, a convolution operator is in the time domain. So this is time domain. Now, when we go to the frequency domain, we begin to talk multiplication, right? So the signals multiply in the frequency domain. Yeah, so we are now going to talk about the switching between these domains. That's why we're talking about the transforms, okay? The Laplace transform, the Fourier transform, and the Z transform, when we now move to the discrete time domain. So we'll talk about the Z transform. Then we also want to determine which domain is best. I just made mention of the time domain and the frequency domain. So we want to know, we want to operate on these signals and whatsoever. We want to analyze the system, want to design the system. So which of the domains will be best for us? So we want to be able to do all of that, okay? Now, we already mentioned quite a number of signals. We have a whole lot of signals, analog signals, digital signals, real signals, complex signals. We have deterministic, which we already mentioned. We have random signals. Then we also have even odd signals and complex signals. Then we have complex conjugate signals, then conjugate symmetric and conjugate antisymmetric signals. We have energy signals, we have power signals, we have neither energy nor power signals, okay? So we'll talk about these things shortly. Now, since we still have a little time in our hands, I'll prefer to introduce us to the MATLAB platform so we can begin to play with MATLAB as we progress in this study, okay? So now we've talked about continuous time signals and discrete time signals. So probably we'll try to see how we'll be able to play with those signals in MATLAB. So any questions so far before I pull this lecture note off and then share my MATLAB screen?
You already pulled it off.
Okay, you wanted to ask a question from there? See, go ahead, ask me. Let's hear what you want to say.
Good day, sir.
Yeah, good day.
Is there a way you can pass in discrete time signals into continuous time systems?
Is there what?
Is there a way you can pass in discrete time signals into continuous time systems?
Then you have to do some. Yeah, you have to do some conversion. I think last session we had to talk about some of the models, okay, that could do those transactions. Okay, yeah, there are systems for that, you know, but we need to do some form of transformation between those domains. You get what I mean? It's all about designing the system. Yeah, so we were able to address that problem in our last session. Now we'll still come to that, okay, as we progress in our study. We are going to talk about some of those models that, you know, can be used for such transactions. Does that make sense?
Yes, sir.
Yeah, and well, do I already put the screen all out? I can just mention a few of them here. I'll just write on this MATLAB, then we'll clean it again. I think if I'm not mistaken, we have the impulse invariance transformation, where we are able to transform the discrete signal Z into a continuous time signal, okay? I think another one is the backward difference transformation, backward difference transformation. Here, we can transform the continuous time signal in the S domain into the Z domain. I think that should be 1 minus Z inverse, yeah, over time period. Or alternatively, we can equally move from the Z, which is a discrete time domain, to the continuous time domain. This 1 over 1 minus S, okay? Then I think we have a third one, which is the bilinear transformation. Yeah, bilinear transformation. Here, we can move from the S domain. So I think we have this, that will be 2 over T. This is 2, not Z. Then 1 minus Z inverse over 1 plus Z inverse. Or better still, we can move from the discrete time domain to the continuous time domain, so that we have 1 plus T over 2 over S, then 1 minus T over 2 S. So once the system runs this algorithm, then, so if we should pass a continuous time signal, it's going to process it as a discrete time signal. Now, if we pass a discrete time signal, it's going to process it as a continuous time signal. So there's a system of such conversion. I don't know if you get what I mean. Is that clear?
No, sir.
No, sir.
Okay. Now, I think someone just asked, well, can we pass a continuous time signal into a discrete time system? Now, we already mentioned that a discrete time system operates on discrete time signal, and continuous time systems operate on continuous time signals. But should we decide to do the opposite, then we'll have to figure out a way of transformation. Okay? So the way of transformation could be through these methods and some other novel methods that may have been, that we may have in the research pool. So that's why you have to go back to the literature and begin to investigate some interesting documentation. Now, well, you have nothing to worry about yet. We haven't got into that. We've not talked about transforms, but Z is used to refer to the Z domain, for which we play with the discrete time systems, and they were able to do Z transform. Why in the time domain, we have the S domain, right? We're going to talk about, I want to begin to talk about region of convergence and where should the pole be, you know, for us to have a region of convergence and all of that. Then we'll talk about all of those things, but I'm just, well, this is more like an introductory class anyway. So we are just running through everything in the course in one day, but we'll still go in depth. And you have all the lecture notes online, so you can always move, at your own pace, okay? So I'll say the lecture notes are on demand, so you can watch them anytime. You can always go back to the lecture notes anytime. So all the lecture notes for this course are already online. Now, what we're trying to say is this: should we decide to design this kind of system, then we can do some kind of transformation. So should I have now the transformation model here is that for given the discrete time domain signal, then this S domain variant transforms it to the S domain. It's more like now, your transforms, your Fourier transform, Z transform, Laplace transform, we are moving either from frequency domain to time domain or from time domain to frequency domain, right? But if you look at this, the impulse invariance, the backward difference, the bilinear transformation, we're actually moving from the discrete time to the continuous time domain, or from the continuous time domain to the discrete time domain. So I want to design a system that, well, I'm going to pass in a discrete time signal into this continuous time domain design system. Then with this algorithm, it should be able to do the conversion for me and process the signal. I don't know if you get what I mean. Did you get that?
Yes, sir.
Yeah, so that.
Yes, sir.
Okay, that's it. So, well,
Yes, sir. Yes, sir.
Okay. So, well, this is more like a MATLAB interface where we have the M file. So I already created this. You can create yours and save it, whichever way. So right now on the M file, I will just type in my code, then I will run. So once I run, then we should get the output. So here, the command line, we are able to also see what is going on. So some of you are already conversant with your command line interface, your Notepad++, whatsoever, your text editor. Okay, so this is my text editor for MATLAB, but we usually save it as .m. So it's an M file. Okay. Now we've talked about continuous time signals. We've talked about discrete time signals. So I want to let's play with it. Let's plot some of those signals. Okay. Now, we use the % sign for comments here. So let's assume I want to pass comments. So once I include my % sign, so it means whatsoever I type here will not be executed, right? So, so this is strictly for comment. This is strictly for comments, right? Perfect. So now it means if we want to execute anything right now, it comes from the second line, right? So let's assume I want to define a signal. So we already know, let's say we have S of t. Oh, let's do this. So let's say we have S of t for a continuous time signal is the same as exponential. So let's it's equal to exponential minus 2t. Let's put it that way, right? This is just a simple continuous signal. Okay, so how do we play with this in MATLAB, and how do we plot the response? Okay, so it means that I'll have to define my dependent variable. This is my dependent variable. Then t is my independent variable, right? So I have to assign values to them. So I have to define the range of values I want to take for my independent variable. Then afterwards, describe the signal, then plot it. Then we'll see what will happen. So for us to be able to do this now, so let's say my time, let's say time t. So I want to take on values from 0 to 10. So I'll say 0. So I want the interval of, let's say 0.01 interval to 10, okay? So now this is more like saying Now what this is saying is, well, my time t, in this case, t is, okay, let me use comments. So let's use comment for that. Let me just, so we expedite action, because we have less than 10 minutes to be, so we don't exceed our time. So let's say I can put up my comment now. What we're trying to say is that 0 less than or equal to 0.0, okay, no. 0 less than or equal to t less than or equal to 10. That's what we are doing here. But the interval will be 0.01. That's what we just did here, right? Good. So now I want to define my signal. So S of t, so let's say S underscore t is equal to, now the exponential parameter or the Euler is going to be ESP in MATLAB, right? Into bracket -2. Then times, we use times t. Then we'll close that, and then we put up the delimiting parameter, the semicolon, to suppress the code. So when we run it, I don't want the code to be displayed. So I'm using the semicolon to suppress it. So I just want it to run without it displaying that code or whatsoever the output of the code is here. Okay. Now I've defined all of this. So I want to plot. So to plot, I just say plot into bracket t, which is that, comma. So we have a lot of options here, comma, separate with the comma, then S underscore t. S underscore t, that's what I want to plot. Now, what is the title? I can also include title into bracket, then then we say, well, this is continuous time signal. Then we close that up bracket, right? Now, I still want to suppress this. Then once I hit the button, let the result come out straight away, okay? Then I want to give my x-axis, so we'll call it x label. Then what do we have there? That's my time, right? Time in seconds, right? Then my y label, that's the y-axis, is my amplitude, right? So amplitude, boom. So we do that. So, well, I don't want it to just print on the blank page. I want to see the grid lines, so I can on my grid on, and that. So once I do this, then all I need to do is to save. So I can hit the save button or Control S. So it saves it. Then what do? I hit the run button. So let's see. So it gave me something. There's an error. Instead of writing grid, I wrote GROD, but my graph plotted, right? But there's no grid line showing. So I have to correct that. So it's not GROD, it's grid, right? Grid. So I save again. So I run. Boom. So everything is fine. So you can see the grid line showing. It's continuous time signal. That's the title we gave to it. We have amplitude this way. Yeah. And then we have the time in seconds this way. And that is the signal. This is a continuous time signal. Is this clear enough, please? Hello?
Sorry, sir.
Please, where is the... Yes, sir.
Yes, what?
So I don't believe we can see the plots, and also the creation of the file. Can you walk through how you create a new file
you didn't
for
see the
MATLAB?
plot.
And we can see the plots. Yeah, we can see the plots.
Okay, so I
think maybe it's open in another window or something.
Yeah, let me share my screen then. Let me share the entire screen.
Okay, thanks, sir.
So can you see,
also,
can you see the plot now?
Yes,
Okay.
we can see the plot. Also, can you walk us through how you actually start up, like how you create a file for, like how you create a new file for this?
Okay, so let us shut down MATLAB since my screen is on. So where is this? Okay, so
Yeah.
so this is my MATLAB. So I'll launch my MATLAB.
Okay, sir.
So this is going to take some time. We have 5 minutes running. So, well, okay. So my MATLAB just came up, right? So, well, this is because I have a number of files open here. So I can just shut these ones down. So that is it, right? Okay. Right. So new. So we want to open up our new file. So I come to this new script. Do you see that? So new. So I have this. So I have to save, right? So if I hit on the save button, it's going to ask me for the directory and all of that. So you can select the part you want to save in and all of that. But I just need, this is class exercise. Let's say PB. Yeah. So I save. So it's going to ask blah, blah, blah program. You don't have permission to save in this location, contact administration. Would you like to save in data erase? Yes. So save. So the file name have changed, right? So now let us do the discrete time. So we already played with continuous time. So let us do discrete time. So say n is equal to 0. We want to take on values from 0 to say 50. So semicolon to suppress that. Then s underscore n is equal to sine 0.2 times pi. Let's say times pi times what again? Let's say times n, because we want to vary s with respect to the values of n that we have defined, right? Then we now want to plot. So for us to plot, remember for the continuous time signal, we use plot, right? Now that I want to do discrete time, we use stem, right? So those are just some keywords you should take note of. N, comma, then we said s underscore n, right? Then we suppress that. So the next thing is to give it a title, right? Title. So this is a discrete time signal, right? Then we want to label the axis, X label. This is just a very simple X label. So what are we going to give to X label? So X is our n intervals, right? So which is our discrete time index. So n, then my Y label. Okay, I can see a hand there. Go ahead, please, talk to me. Y label is still my amplitude.
Simply, what is it used for the stem?
Is to plot discrete time signals. Is the now when we plotted continuous time signal, we used the keyword plot, right?
Yes, sir.
Yeah. So here, plot is for continuous time signal, as stem is for discrete time signals. Okay.
Okay, sir.
Yeah. So then that. Then what else? We want to on our grid, right? We wrote GROD the last time, so we don't want to make that mistake again. So we on the grid. So now we can save, right? So let us run. So it's going to ask for a path. It's going to ask me for a path. Okay. So change folder. So I just add to path. Okay. And boom, we have our discrete time signals. Does this make sense at all?
Yes, sir.
Okay, so
Yes,
now you see your MATLAB tool is very good.
Sir,
Yeah, go ahead, please. Yeah, go ahead.
so the values that are showing up, is it run by the computer? Or...
No, I assigned the value. The range is 0 to 50 for n. I gave that 0 to 50.
X.
Right? Why I
Yes, sir.
define the relationship. Assign this 0.25 this. So it varies by changing value of n. When n is 0, it gives me 5. When n is 2, it gives me the value. When n is 3, Then when n is 50, so it plus that relationship.
Okay, sir. Thank you, sir.
Okay, so we just concluded our activities and hope the class was interactive and interesting.
Yes, sir.
Yes, sir.
Okay. So
We enjoyed it so much.
okay,
Thank you very much.
So
Thank you, sir.
you're welcome. So I think now you can all say you know how to use MATLAB. So you begin to play with MATLAB. So I probably in subsequent lectures, we'll see how to implement some of these things in Python. And then all the way you can take things up going forward. So let's see how we can get our hands dirty to get a good job done. So I hope to see you in class.
Thank you, sir.
So bye for now.
Sir,
Okay, go ahead.
sir, please, was the video saved so that we can practice more often?
Okay, yeah, I'll try to upload this video as class interaction. Well, just because the video should be very, very messy, right? So we had a lot of interaction. So I'll put it up. I'll upload it to the channel.
Okay.
Thank you, sir.
Thanks, sir.
Thank you, sir.
Okay, so do have a great day and bye for now.
Thanks, sir.
Okay, thank you, sir. Bye-bye. Thank you very much for the class.
Yeah, bye for now. You're welcome.